This next session, our speaker is going to be Daniel Sun. He's the Vice President of Intelligent Vision Business Unit at Thundersoft. He would just tell me a little bit about Thundersoft, just amazing company with global presence. Daniel and I share a mobile industry background. Both of us, I think, have been in the mobile phone business for more than a decade, so interesting to meet people that have similar backgrounds. So with that, I'll introduce Daniel.
Thank you. Thank you. Today my presentation will be more focused on operating system optimization around the vision, embedded vision and AI. I will give some case studies and especially focus on the camera, image processing, and also AI algorithm. Well, a little bit on the Thundersoft. Thundersoft, we have dedicated units, business line, work on we call it intelligent vision. The reason we call it intelligent vision is that traditionally we call it computer vision, but nowadays with AI, we start to make it intelligent. That's why we call it intelligent vision. But basically it covers all the engineering activities from camera drivers, camera framework, and the camera tuning, image quality tuning, whatever you call it, IQ or PQ, and also some algorithms, image processing algorithms, and also computer vision, and also AI stuff. That also extend to camera applications. Well, in my presentation, I will quickly go through a few case studies, list some embedded vision challenges, and also some case studies of system optimization, especially now very fragmented embedded environment and chipset. And in the final part, it will be more about embedded AI challenges. Let's look at a very high-level vision architecture today in the embedded environment. So if you look at this, it's quite a complex architecture. There's also kernel space, user space, video for Linux, camera API, plus a key part would be the 3A algorithm, including autofocus, auto exposure, and white balance. So there's also a fine-tuning of image tuning data. And above this would be multimedia codec, then we have applications. But a camera outside this, there's also some video analytics engine. This is a high-level architecture. Well, let's look at the challenges. The first is a good quality vision system. There's many impact factors. For example, how do you choose the modules? It's had different optical characteristics. There's a lens difference. There's also autofocus. There's also modal difference, and the drivers, and also the 3A, different mobile chipset, different IoT chipset may probably have different 3A algorithms. And also there's HDR, there's low noise, low light, noise reduction, etc. And also camera framework is also different. There's also different ISP tuning tools. There's so many factors which are impacting the good vision system performance. Second would be, today, if you look at this hardware, there's so many different chipsets. The fragmentation of hardware also require quite a good know-how to do image quality tuning. I will explain later on what is image quality tuning and why it's so important. There's also quite a complex tuning process. Then another challenge would always be coming from power consumption and performance. Then the last is that we have quite a few rich experience to fix those issues, which are explained later. Well, the first, let's say some challenges around automotive. For example, if we look at automotive, there's some applications like ADAS, like CMS or surround view. You have 4 cameras you need to stitch together. So now it's quite important to have 4 camera harmonization so that you reduce the artifacts in the overlapping area. Then the brightness, the color, over 4 cameras, harmonization is very important. So in that case, we also need a quite good AE and AWB accuracy. And we also need some good tools on PC to tuning multiple cameras. For example, if you are doing surround view with 4 cameras, you need to tune the 4 cameras at the same time. So you need a good camera framework, a good ISP tuning tool, and also a good accuracy. For example, if your car out of tunnel, the fine tuning of WDR and AE is extremely important. Because when you go out of the tunnel, there's a backlight. So auto exposure convergence must be very quickly converged. Else you have some problem. No matter your AR or not AR, if the basic sensor has some problem, you just will have some issues. And another example would be sharpness of the image is also very important. If there's a blur, so that may have some impact on your AR accuracy. So that's why a fine tuning of the image quality for automotive use cases are very important. And another example, which I already mentioned, would be the surround view use cases. For example, today more and more automotives, we start to use raw data or bare sensors. So in that case, the 4 sensors, you have to calibrate, you have to make it harmonized in terms of brightness or color in order to reduce the artifacts when in overlapping areas when you're stitching them together. So all of these are also important to make a good user experience. Another area for embedded vision, a very typical needs would be for to maximize the value of your hardware, especially there's GPU and a DSP. I just give some examples. So today, in the majority of the chipset, you could have image processing, and post-processing, and in each part of them, there could be different use cases. And for GPU, I could have some examples. For example, the first one, you would say there's the WAP. For example, stitching, there's 2 fish eyes. Sometimes you want to make a 360 view. In that case, the shading and the warping would be big issue. So the typical would be you put the warping in the GPU to achieve a quite a good performance. And another area would be DSP. For example, you could put the 3A in the DSP or even MCU in order to achieve power efficiency. So there's also a lot of image analytics and also other algorithms which you may consider to put in the GPU or DSP. Well, next would be, I want to mention a little bit about image quality tuning. So tuning looks like, it's very fragmented because, different phones, different, IoT devices, different automotive. You may choose different lens, different modules. So in that case, to maximize the value, the performance of the whole system, they require very good image quality know-how, tuning know-how. So in Thundersoft, we have the industry best class image quality team with over 17 years experience. And we have a large team in Bulgaria, which have quite a good experience. And we have the state-of-the-art camera labs. So image quality tuning, what is that? In fact, the core of IQ tuning is to tune all characteristics of image pipeline. Image pipeline is also complex. And the 3A algorithm, the 3A including AF, autofocus, and AE, auto exposure, and AWB, auto white balance. So it may include, for example, the typical characteristics, for example, the brightness, contrast, white balance, color accuracy and saturation, focus, detail texture, or noise. So just some examples of, if you tune, well-tuned vision system image and you don't tune it, there's a big difference, in fact. And also more examples with good IQ tuning and no IQ tuning. So how we tune is this? Basically, you need to do some software because tuning itself depends on some basic stuff like software baseline, software functionalities. You have to check, make sure that the driver is well developed, and there's no major defects in the driver which blocks the image quality tuning process. So I have to verify the raw capture, raw data, EXIF, AE parameters, and also the module calibration data, which are well defined. Then this is the first stage. Then you start to put in the lab. We have our studio. There's a lot of different equipments which you start to tune in the lab. For example, RSA, EWB, AE, gamma. There's a lot of characteristics where you need fine tuning. And the last step is that you need to go outside of the lab to go to real life because people use whatever is mobile phone or use automotive. You have to apply on the real life. So that's why a real life tuning, a few testing of the device, of your vision system is also quite important. So we define a lot of things side by side with reference cameras. So that may cover people, landscape, pets, portraits, outdoor, low light, even concert, bars, and foods, a lot of things in order, to have the best trade-off and balance of the camera parameters. Now let's start to talk a little bit about the AI. So today, a lot of companies doing AI, but it's a cloud-based or a server-based training. After that, you need to do inferencing. But if you put AI on the embedded environment, there's always a challenge of, first, a very limited computing power. And then there's a thermal issue. I've been experienced that take a face recognition on, for example, Samsung S8. If you're running it on the CPU for a long time, it's become very hot. Then but the problem is that the typical way is, you trim the network. You reduce the layers, and you compress whatever in order to make the model smaller. But their accuracy will be another issue you have to balance. And another issue would be the ecosystem. So every chipset vendor has their ecosystem, whatever it's a Qualcomm, MediaTek, or Intel, or NVIDIA, or any other AI chipset, acceleration chipset, or DSP, FPGA. Everybody has their AI middleware. So as a vendor, you have to port your algorithms on specific AI middleware. It's a different small ecosystem. So let's look at how typically we put it on the embedded environment. So first, you have to understand what is your target chipset and what is the estimated performance and what is the computing power you have. Then you have to set a complexity upper bound. In that case, you start to have your network trained based on those constraints because you don't have enough computing power. It's not on the cloud. It's not a big server. It's a very, very small embedded chipset. In that case, you already achieve the actual performance or FPS, whatever other KPI you're going to achieve. After that, you have to train and test your network, and there's an iteration of this until finally you balance the best between the thermal control, the performance, and also the accuracy. I would say it's a optimization, and to make a model is quite easy, but it's primarily to commercialize a model, it's better fit in the embedded environment to meet the performance requirements, to make very stable with a quite a good thermal condition and also reach the accuracy is absolutely not easy today. Well, so other case studies for optimization for embedded AI would be that we could customize the AI model and operate some operators based on Haskell, DSP, GPU, or CPU instruction sets. And also there could be some assembly code you can write to optimize some image processing steps, like, for example, skew, rotation, crop, for better performance. I'll just give some example. For example, Qualcomm 820, you can write some, assembly code, which you can optimize on CPU. You would say that after optimization, if you use DSP HVX, you could see the performance can be greatly improved. That's why on the embedded environment, this is the real data we measured. On the real embedded environment, it's very important to optimize your system software on the DSP or on GPU, on whatever you can have, rather than CPU only. Another area I would say on the embedded environment would be now for a good vision system, a good image quality, AI start to really contribute to that. I'll just give a few examples. The first would be, for example, the scene detection. Today, if you look at the majority of the phones on the market, you only have one camera parameter, which are in fact the trade-off of all the real-life scenes. So that require multiple months of engineering to tuning inside the labs. So there's always a trade-off. For example, in the low light condition like under the table, if you suppress the noise too much, sometimes you lose details. But the problem is that if you keep too much details, you have noise. Sometimes you just cannot, you just balance. Some people, it's quite subjective. Some people say, I would like to see more details. I don't care a little bit more noise. But some people feel that better to suppress a little bit noise and also sacrifice some details. Now, but if you look at the first example, like fireworks, now we also develop, for example, some AI algorithms running on 845, for example, the DSP, which are power-friendly, some AI algorithms, which can detect now, okay, it's a fireworks. For a normal consumer, a lot of people, they just don't know how to change the menu, set the settings for specific things. They just want to take the camera and take good photos. If you look at it today, majority phone, the high-end phones, the camera itself, the hardware, the sensors, are already quite good. Why sometimes you cannot take a good picture? Just because it's not a real physical digital camera where you can at least play with that. Because there's a lot of menus, there are a lot of settings are hidden, which you don't know how to configure, or you don't have time to configure. You just want to capture the moment. Now with AI, you can detect the scene and apply a specific camera parameter on that. So everybody can take a good photo. It's the same for a sunset, for other, pads, or office, or there's power. Other areas where AI start to contribute a lot would be, for example, HDR. Traditional HDR just, take 3 or more frames with different exposure. You're just using some image processing algorithms to merge them. That's it. But that's not enough. If you look at the phones, you take a photo in a big light, even iPhone or other, top phones, still there's a big issue. You just cannot get an ideal picture. Now with AI, you could have a lot of, frames where you can selectively merge, you can recognize things. And also another area would be noise and a low light improvement where a lot of people start to use AI. Okay, conclusion. Today, the operating system now, even are dominated by Android and Linux, but still with a lot of more features, multiple cameras, fragmentation of chipset, fragmentation of different sensors. To have a good vision solution, there must be optimization of the system software. But this also depends on the different use cases. That could be a smartphone, that could be IoT, that could be automotive, it could be surveillance. Depending on the use cases, now you have to optimize the system software in order to achieve a good vision solution. Second is that we shall always check carefully our chipset where we shall fully leverage some special computing architecture like GPU or DSP. DSP is more, power friendly. And if there's an AI chipset, that'll be better. So it's more efficient. And the third would be fine tuning of the image quality is quite important. It just cannot, just install a sensor, a camera, and make a good image quality. There's also require a multi-months of fine tuning in order to squeeze, the performance out of hardware. The last thing is that AI is really now converging with traditional image processing algorithms to contribute a better user experience. Yeah, so that's all for us. Thank you.
Thank you, Daniel. We have a few minutes for questions. If you have a question, please step up to the mic in the aisle.
Hey, Daniel, thanks for the talk. When you spoke earlier about image quality, are you talking about the quality of the image needs to be good so that when you feed it to your inference, it responds with more accurate results, or is it image quality simply for image quality's sake to get, using AI to make a better camera?
Yeah, so image quality, when I talk about it's a general purpose image quality. You just take pictures, they good image quality. But interestingly, there's traditional image processing and AI. In fact, the AI does not require a so perfect input today. For example, the noise. It does not mean that you need a very high resolution or without any noise, a perfect image quality, so you could have a good AI algorithm. In fact, AI is not so sensitive to those even noise. But sometimes, as I mentioned earlier, that the blur or flare of the image quality may have some impact on AI.
Okay.
But another direction, for example, in order to have a good image quality, AI start to contribute to that.
Right.
Yeah.
So just a follow-up question. With the image quality, you mentioned use of DSP.
Yeah.
Do you also involve use of optics in image quality, actually the camera, or do you recommend using software image quality like FFmpeg to, create, for better brightness and modification, that sort of thing?
That is more for a software, because once you fix a BOM of the smart devices, the optics definition has been fixed. In that case, you have to rely on software to achieve a better user experience or better image quality. That is more software.
Okay, thanks.
Yeah.
Hi, Daniel. I liked your presentation. Along the same question about image quality, I'm just seeking the next step in clarification. You mentioned the pain and iterative process of camera pipeline tuning, and I know you guys merged with MMS, and you have the best team in the world doing that process. It looked like on the next slide you were suggesting, though, that AI could be used to circumvent some of that manual tuning process by learning what the target is. Is my understanding correct? Is that what you were trying to express by using AI to shorten and simplify the IQ tuning process?
Yeah, that could be possible in the future that AI may automate part of the image processing, image quality tuning process. But today, seems it's still a little bit difficult to make it fully automated. So, but in some areas like HDR or specific cases, AI start to contribute to that. But this is still in the exploration phase.
Okay, that I understand.
All right, well, let's give him a round of applause. Thank you, Daniel.
Thank you.